Now that we've introduced algebraic vectors, we're going to go through all the things that we can do with geometric vectors and how we do them when we're dealing with vectors in component form or algebraic. So we learned about scalar multiplication and addition and subtraction of vectors, how to do that algebraically. And as it turns out, most of the operations are very simple. Now I'm going to give my examples with my vectors in 3 space, okay, in R3, which means there'll be 3 components, x, y, and z. It's simple to apply these definitions to vectors in 2 space. You just kind of ignore that third z coordinate and you're dealing with the exact same thing. In fact, you might even say that 2 space is really just a special case of 3 space where all your z values are equal to 0 or something like that. So we'll start with vector equality. Not a surprise here. If you've got 2 vectors u and v, they are going to be equal if and only if all 3 of their components are exactly the same. Clearly, if they have one component or vector number that's different, then they're not the same vector. They're not going to land on the same point. Notice I've chosen to define the vectors a1, b1, c1, a2, b2, c2. You can kind of do whatever you want here. As long as you use subscripts here, those are obviously not exponents. You could do u1, u2, u3, and v1, v2, v3, that's common as well. I just find my u's and v's start to look a lot alike. Okay, so there's vector equality. Scalar multiplication. If you've got a vector, I'll call this one ABC in R3, and a scalar KER, then KV is K times A, K times V, K times C. So basically just take your vector, and if you want to triple it, you just multiply each of the components by 3 or whatever number it is. And that's not surprising either if you just imagine a vector. If you wanted to, if you want to triple or double, let's say double the magnitude of this vector, well, doubling each component will do that. You can kind of imagine it in 2 space a little bit easier. If you think about, having, that should be an arrow, but having, you double so there's your this vector is made up of your x and your y. And if you want to double that vector, well, doubling the x and doubling the y again is going to be what doubles that vector. The same thing with in 3 space. It's just kind of like a 3-dimensional staircase if you want to think of it that way. Addition and subtraction. Adding algebraic vectors or subtracting algebraic vectors is just a matter of adding their components together. And it's very similar to this idea right here. If you imagine the vectors being, head to tail, okay, we know the sum of these 2 vectors is the vector that's created right here using the triangle law. Well, really, you would get that vector just by following the components, taking all the components of the first vector and adding the components of the second vector. Pretty straightforward. We can then combine what we learned about addition, subtraction, and scalar multiplication to answer something like this. So suppose u is this vector 3, 1, 0, v is 1, negative 1, 3. Find 3u plus 4v. Well, that to be 3 times 3, 1, 0 plus 4 times 1, negative 1, and 3, which is equal to 9, 3, 0. Okay, triple all those, plus 4, negative 4, 12. And then to add those vectors together, we just add the components here. Gives us a final answer here of 13, negative 1, and 12. Done. So hopefully most of those operations are pretty straightforward. Here's something that's a little bit different, and this is a vector joining 2 points. So geometrically, we didn't really do this. But what happens is vectors can be very useful in analytical geometry. And what I mean by analytical geometry, is if you're dealing with points on the XY Cartesian plane or the 3-dimensional XYZ coordinate axis, then vectors are useful at solving problems in geometry. So what we're going to do here is we're going to show how do you create a vector that joins 2 points together. So before I walk through this definition, let me just give you an example with some numbers. So here you see I have 2 points. I've just made them up randomly and graphed them. And I kind of need to work in 2 dimensions here because in 3 dimensions it's just hard to show, but it's the same kind of idea. So suppose this is point P and this is point Q. Okay, there is a vector that exists from point P to point Q, a point-to-point vector, and there I've drawn it there, it's PQ, from P to Q. Now, we don't draw vectors like that. Vectors can exist in, I mean, we can think about vectors in positions like this, but vectors always, they don't have position, they have magnitude and direction. So PQ should not be here. Vector PQ should be down here. And vector PQ is described by this point right here, which is actually 5, 2. So vector PQ, the vector that joins point P to point Q in that order, is 5, 2. Now, how do I get that? Well, it's actually not that hard to see. If you think about it, it really, where did I get the 5 from? Well, 3 to -2. It's kind of like a rise and a run thing. Okay, I ended up at 5 because the distance from -2 to 3 is 5, or 3 subtract -2 is 5, like kind of like doing slope. And how did I get 2? Well, the difference between 4 and 2 is 2. So the vector PQ is equal to 5, 2. It is very similar to calculating the slope of a line segment. So we can see in general that in R2, if we want to join points P and Q, the vector PQ is just going to be equal to A2 minus A1, which is kind of like your run, and B2 minus B1, which is kind of like your rise. And that picture shows it very, very clearly for one example. Now, if I move into R3, I add an extra component. Well, now it is, although it is harder to visualize, you kind of got to imagine the possibility that point Q could come like out of the screen or into the screen. And that means that along with calculating a rise and a run to get 5, 2, you'd also subtract their Z values to kind of find the distance that the points, the change in that third direction coming in and out. So it's a little bit hard to visualize, but it's not too bad. And so vector PQ in 3 space is basically calculated the exact same way. A2 minus A1 and B2 minus B1 followed by C2 minus C1. And these are very powerful tools for working with points, especially points in 3 space. When you want to figure out properties of geometric figures on the x, y, z coordinate axis, vectors we're going to find are very powerful for doing that. In fact, is really the whole point in learning this material. Now, please notice the order of subtraction does matter. If you were to switch and do A1 minus A2, B1 minus B2, and so on, you wouldn't get vector PQ, you get vector QP, which is the exact opposite direction. So the order of subtraction does matter, assuming you want vector PQ and not vector QP. And sometimes you don't care, it does depend on what you're doing. Next, let's talk about parallel vectors. What does it mean if 2 vectors are parallel? Well, it basically means you've got 2 vectors that have the same direction. Now, this picture is a little bit misleading. We'll talk about that in just a second. So 2 vectors u, v are parallel if and only if it must be the case that one would have to be a scalar multiple of the other, because they have the same direction, they just have possibly a different size. And if one is a scalar multiple of the other, it means that something like this, u must equal k times v for some ker. So for some real number must exist such that vector v can be written as a multiple of vector u. Now, it could be the other way around. It doesn't matter. Like in this picture, u equals kv. It just means that the k value has to be less than 1 since u is shorter. It looks like it'd be like 2/3 or 3/4 or something like that. As an example, suppose we want to know, is vector AB parallel to CD given these points in 2 space? So we need to start by finding out what those vectors are. AB would be the vector, so be the vector 6. I'm sorry about that. No, hang on, I got the wrong number there. 3 subtract 2, okay, and 6 minus 0. So AB is really the vector 1, 6. And then we do the same thing for vector CD. Take the D coordinates and subtract the C coordinates. So that would be, let's see, 5 minus 3 is 2. And negative 5 minus 1 is negative 6. Next, to determine if the vectors are parallel, we say, is there a K such that AB is equal to K times CD? And it doesn't matter which order you do that in. It could be CD equals K times AB. It doesn't matter. Well, let's just think about what that would look like. Well, that would mean that we would have something like 1/6 must equal K times 2 negative 6. And we're going to find that answer is no. And the reason that the answer is no is that, I mean, if I look at the 6 and the negative 6, it must be that K is -1. Well, if K is -1, then I would expect to see a -1 here, and I don't. I have a +2. If I looked at 1, 2, it would mean that K must be a half. Well, if K is a half, then I would have a +3 here. So there's no way. The answer to this question is no, that those vectors are not parallel. Notice that, like, I mean, it's really the same question as, is line segment AB parallel to line segment CD? Normally you would use slope to answer a question like that. In this case, you're just using vectors instead and realizing, are the vectors scalar multiples of each other? Is one just a multiple of the other, meaning that they have the same direction? Now, slope works in 2 dimensions, but slope doesn't work in 3 dimensions. There's no 3-dimensional slope. Instead, we just talk about 3-dimensional vectors. So this question in 3 dimensions isn't any harder, even though there'd be no other way to do it. Okay, now as I was going through this example, I was sort of like shuddering a bit because the word parallel is not used for vectors. Okay, and the reason it's not used is, like, look at vectors u and v. They sure look parallel, but guess what? U and v don't have position. They just have direction and magnitude. So really, vector u is on top of vector v. So we don't think about them as being parallel. We think about them as having the same direction or being what's called collinear. So collinear is the word we use for parallel vectors. Going forward, please don't use the word parallel. I mean, this is ugly. Ugh. A parallel symbol between 2 vectors? No, we just say that they're collinear. Or we say that AB equals K times CD if they are, meaning that they are collinear, can be drawn on top of each other or are on top of each other. Okay, parallel vectors have the same direction or opposite direction, I should actually say. So collinear means they could be the same direction or opposite direction. Let's even do this and say that this should really say we're talking about collinear vectors. Line segments can be parallel because they're not on top of each other. Line segments have position. Okay, line segment AB has a position on a graph. Okay, like, you know, right here, let's go back to this example. PQ, line segment PQ has a position, but vector PQ does not have a position, or actually we say its position is really down here at the origin. So even if I started making other point-to-point vectors here, okay, so maybe there's one here. No, it's not here. Okay, you've chosen to draw it here because it might represent this, you know, the vector joining 2 points here, but really this vector is down here as well. They're all down here. They all have their tail at the origin. In this next little example, we're going to talk about how you can use vectors to work in analytical geometry. And when I talk about analytical geometry, I just mean working with points. So we're saying 3 points, A, B, and C, are collinear, means that they can be drawn in the same line. So points can be collinear as well, if they can all be if a line can be drawn through all of them. If and only if the vector from AB is equal to some scalar multiple of the vector from B to C. So what we're doing is we're using vectors here, so this is the vector part, to determine something about points in space. And those points in space have nothing to do with vectors. So I actually found this cool website, and I'll post a link for it for you guys, but for now I can just show you what it looks like. So this is a little 3D plotter, and I plotted these 3 points. You can pick whatever points you want. It looks like you can graph planes as well, which we'll get into later. And you can move the axis around. You can see where these points are. You can change where they are, of course, and do that kind of stuff. So, okay, I'll stop playing here. Now, if you think about it, you can draw a line through any 2 points in space. Okay, so I can connect these 2 points. I could connect these 2 points. I could connect these 2 points. But I can't necessarily draw a line through all 3 points. In fact, you can tell very clearly that these 3 points I've just made up randomly are not collinear. It doesn't look like you're going to be able to draw a line through all 3 points. You can see that pretty clearly. The same thing happens in 2 space. If I go back to this example, any 2 points I made here, I can draw a line or a vector through them. Okay, but a third point may or may not belong to that line. So if I draw a third point here, these 3 points would be collinear, but if I made my third point up here, they're definitely not. So let's apply this as like a theorem. Let's apply this theorem to this example with these 3 points. Determine whether these 3 points in space, whether we could draw a line through them all. So we start by finding vector AB. Okay, we do that again by subtracting the vector numbers in B, subtract the vector numbers in A. So -3 minus 9 is -12. 2 subtract -6 would be 8. And -5 subtract 15 would be -20. We do the same thing and find a vector from B to C. Subtract the coordinates of C from the coordinates of B. So I get 6 subtract 9 is -3. -4 subtract -6 would be 2. And 10 subtract, oh, I think I made a mistake there. My apologies, let me back up there. I think I was using point A by mistake. So 0.6 subtract -3 is 9. -4 subtract 2 is -6. And 10 subtract -5 is 15. That looks better. So then next we say, can I find a K such that, mathematicians get tired of writing such that, they actually use ST a lot, such that AB is equal to K times BC. Or, using the numbers that we have, that means that does -12, 8, -20 equal K times 9, -6, 15. Let's just take a look here. So, I mean, I can try to solve this and just do a little bit of work up here. -12 would have to equal K times 9. Well, that would tell you that K must be equal to -12 divided by 9, which would be -4/3. And it sure looks like that will hold for all of them. It does. So 8 times -4/3 would in fact give you -6. And -20 times -4/3 would in fact give you 15. So that does work. So the answer to this question is yes. The points are collinear. They can be drawn in a line. We can draw a line through all of them. So the question had nothing to do with vectors. We just used vectors to answer the problem. And I mean, this should kind of make sense what's going on here. I've actually plotted those 3 points, A, B, and C, in this little 3D plotter. And you can see that the red point is point A, the yellow point is actually C, and this is point B down here. Sure, looks like they can be drawn in a straight line, and they are collinear. We figured that out. But what we did to answer this problem is we found the point-to-point vector AB, which is the vector that we think of as going from here to here. Okay? And then we took and we figured out what vector BC was. And vector BC went from here to here. And then we compared those vectors and found, sure enough, that they were in fact collinear vectors. AB was just some multiple of BC, which means the points must line up in a straight line. If, for example, point C had been like off of it, like maybe point C was adjusted so that, you know, its Y value wasn't -4, maybe it was like, you know, +1 or 0 or something like that, well then then vector BC would be like this. Okay, and they wouldn't be scalar multiple of each other because point C is not on the same line that AB is. Now keep in mind too, although I've drawn, it's convenient to think of the vectors out here like this. In reality, when we figure out vector BC, we're actually figuring it out. I mean, the point we get is if the tail is at the origin. Okay, and when we figure out AB, the point that we get is actually if the vector's tail, again, was at the origin, like, let's not let me do that, like this right here. Okay, it's not useful to think of it this way, but that's what that point, the coordinates AB, that's what they represent, and same with BC or whatever it is we figured out there. So just something to keep in mind. For the last part of this lesson, we're going to discuss unit vectors. And we've talked a little bit about unit vectors already, and we've discussed the symbol. One thing I should mention is if you have this symbol right here, it implies that V is a unit vector. But not only that, it implies that it's a unit vector in the direction of vector V, assuming vector V exists somewhere else in the problem. Okay? Any vector V can be expressed as a scalar product of its magnitude and a unit vector having the same direction. So for example, imagine you had vector V, and let's say that the magnitude of V, we'll keep it simple here, that the magnitude of V was equal to 3. Well, that basically means that V, it could really be expressed as 3 times, I'll try my best to draw 3 here, that's not very good, but I think you get the idea. That vector V is really just 3 times a unit vector in the same direction as V. In general, we can say that V is really the product of its magnitude times a unit vector in the same direction as V. For example, to keep it really simple, we've got vector V being 4, 3. So the magnitude of V would be equal to the square root of 4 squared plus 3 squared. That's a 3, 4, 5 triangle, which is just 5. So we can say that really vector V is equal to 5 times a unit vector having the same direction as V. Now this is a little bit strange, but I am going somewhere with this. It also means that a unit vector in the direction of V is really equal to V divided by 5. Now how do you divide a vector by something? Well, it's just scalar multiplication. It's really just a fifth of V. Oh. It's really just 1/5, a fifth of vector V. So we can rearrange the same way I rearrange this. We can take this and we can really say that a unit vector in the direction of V is really just a vector V divided by its magnitude. So the long story short here is we can take any vector we want and we can find a unit vector in the same direction as that vector. For example, vector V here that had a magnitude of 3, if I took vector V and I divided it by 3 or multiplied it by 1/3, I get a unit vector in the same direction as V. And that's important and that's used a lot. It's called normalizing a vector. So there's a new term for you, normalizing a vector, creating a unit vector that has the same direction as another vector. So for example, I can normalize this vector by coming up with a new unit vector in the same direction. And I do that by applying this definition. So a unit vector in the direction of V will be the vector V 2, -3, -6 divided by the magnitude of V, which is the square root of 2 squared plus -3 squared plus -6 squared. Okay, that gives us V being 2, -3, -6 divided by the square root. Now that we understand unit vectors and algebraic operations with vectors, we're actually going to talk about unit vector notations. This is a different notation for talking about algebraic vectors. In R2, so in 2 space, we of course have the x and y axis. And we define 2 unit vectors in the direction of both the x and y axes. So the first unit vector is called I. It is equal to the vector 1, 0, which it just puts I right here. And the second one is j. And j has the same direction as the positive y-axis, so it's 0, 1. So j goes this way. And that means we can, and unit vector notation is defined using I and j. So instead of seeing 4, negative 8, that would be 4 times I minus 8j. Another way of talking about an algebraic vector. I'm not a big fan of this notation. You should be comfortable with it. It does exist. I mean, just think about it. If you plug in I is 1, 0 and j is 0, 1, you're going to get 4, negative 8 here. So you should be comfortable seeing vectors written like this as well. In R3, we can do something very similar. Of course, now we have sort of x maybe this way, y this way, and z coming up. So that we're in 3D. We use I now. It's going to have to be 1, 0, 0. So that puts I this way. J is the direction of the y-axis still. So 0, 1, 0 puts vector j right here. Notice these definitely have a magnitude of 1. You can tell just from the picture. And then, not surprisingly, we use k for our last unit vector, 0, 0, 1, which puts k in the direction of the positive z-axis. So these are called the standard unit vectors, or sometimes called the standard basis vectors. We'll get into that a little bit later. So any vector that's expressed like as in terms of its components like this can also be expressed in terms of I, j, and k. So this would be the same as the vector I minus 2j plus 7k. So if you see a vector in this form right here, you can always change it to the other form if you want. It doesn't matter. We're going to finish this lesson off with a proof. Yay. Remember that there were lots of properties of vector addition and scalar multiplication that we discussed, and we did that geometrically. Now we have algebraic vectors, which are the exact same. So we can use algebraic vectors instead of geometric vectors. And a lot of those properties that we discussed are very easy to prove using algebraic vectors. One of them that we didn't prove was the distributive law. So scalar multiplication and vector addition are distributive, meaning you can distribute scalar multiplication over vector addition. We didn't show that geometrically. It's a little difficult to show geometrically. It's very easy to show using components. The hardest thing is just getting set up. So how do I show that this is true? Well, I define A and B as algebraic vectors. So I'm going to say let A equal A1, A2, A3. And B equal B1, B2, B3. I'm proving it in R3, okay? And if it's true in R3, it's going to have to be true in R2, because in R2 you could just imagine that the z value is always equal to 0, the third component. So the easiest thing to do is to break this equation up into its left side and right side. Okay, starting with the left side of the equation, we then will actually put the vectors in here. So the first vector, A1, A2, A3, plus B1, B2, B3. Next, we are going to actually add these two vectors. We know we can add two vectors just by adding their components. And let's see if we can do that. Okay, so we added the A1s to the B1s, A2 to the B2, A3 to the B3. Okay, and then finally, our next step is to actually multiply. This is a vector now, a single vector. And we're going to multiply it by k, and we do that by multiplying each component of the vector by k, like so. And that's what we get. So a single vector, where the first vector number is k times a1 b1 plus b1, k times a2 plus b2 for the second vector number, and the third vector number is k times a3 plus b3. Now inside of, up here we did vector addition, okay, from here to here. I think that's important to understand. But in here, this is just a number now. So although this right here is a vector and this is a vector, the components are just real numbers. So these are all just real numbers now. So they obey properties of real numbers, which means I can expand k over the addition, and I can do that for each component. So I'm basically simplifying the vector numbers themselves. And here's what I get. Okay, ka1 plus kb1, ka2 plus kb2, and ka3 plus kb3. I don't think there's anything else I can do with that. So that's basically the simplified vector when you do this right here. So for the second part of the proof, I know this is long, we do the same thing with the right side. So let's do that next. So the right side is ka plus kb. We're going to sub vectors a and b into this equation. So vector a, of course, was a1, a2, a3. And vector b is b1, b2, b3. Once you get this set up, I think the proof kind of does itself, to be honest. Okay, we're just going to multiply vector a by k and vector b by k. Okay, so we multiply each vector number by k for both vectors. And then finally, we're ready to add those, and we just add components. These are two vectors now. Vector addition is next. And there you have it, our final simplified vector. And sure enough, the right side of the equation and the left side of the equation are the exact same thing. And we have, in fact, proved the distributive law for our vector addition using component vectors. It's long, but boy, it once you get it set up, once you get the idea of starting the proof off by defining each vectors in their component form, just a matter of doing the math. Okay, that's it for this lesson. Thanks.